Hi everyone, we are Group 6 and today we are presenting our Indoor Environmental Quality or IEQ assessment of the FPE Resources Center in UNIMAS. IEQ is a critical part of building science that affect our health and productivity. We focus on our main area, air quality, thermal comfort, lighting, and acoustic. Our main goal were to measure on-site IEQ, benchmark the result against MS 1525 and ASHRAE standards, and suggest practical solution for any issue found.
The selected case study is the Resources Center at the Faculty of Built Environment in UNIMAS. It is an enclosed air-conditioned learning space with a floor area of 2,013 square meters and occupancy of up to 80 students during peak hours. The space used 5 centralizer air conditioning units, 46 LED bulbs of 80 watts, and an open plan layout. However, hard interior finishes and limited acoustic material contribute to higher noise level and sound reverberation. Various instruments were used in the Indoor Environment Quality IEQ assessment to evaluate indoor air quality, thermal comfort, lighting performance, and acoustic condition within the Resources Center. First, the ASHRAE 7755 handheld CO2 meter was used to measure carbon dioxide concentration. The device was switched on and placed at the height of 1.2 meters, representing the occupant breathing zone. Readings were taken under both occupied and unoccupied conditions after allowing the sensor to stabilize. The step-by-step measurement procedure is present in the table beside. Next, a mini particulate counter was used to measure PM2.5 and PM10 concentration. The instrument was positioned at the same height and reading were recorded after a 30 seconds sampling period. The details procedure are also shown in a accompanying table. For thermal comfort assessment, a handheld thermal imaging camera was used to capture temperature distributed within the space. Measurements were conducted under two conditions, with the air conditioning system switched off and switched on, allowing comparison the thermal performance. The results are provided in the table. In addition, a Testo 610 thermohygrometer was used to measure relative humidity and wet bulb temperature while the air conditioning system were operating. Measurement steps are shown in the table beside. For light assessment, a 10 miles TN 2009 lux meter was used to measure illuminance level under natural lighting, combined lighting, and artificial lighting condition. The instrument setup and procedure are included in the table. Lastly, an NTI XL2 acoustic analyzer was used to measure background noise level and reverberation time using the balloon pop method. In order to evaluate the acoustic performance of the Resources Center, the procedure for these measurements are also shown in the table.
According to ICOP-IAQ 2010, the recommended carbon dioxide level should remain below 1,000 ppm. Under the unoccupied condition, points 1 to 4 recorded average values between 756 to 790 ppm, and all points achieved the standard. During the occupied condition, the average carbon dioxide levels increased to around 860 to 850 ppm due to human respiration. But all points still remained below the 1000 ppm limit, showing that the ventilation system was effective and complied with the standard. Particulate method. Fine particulate concentrations for both PM2.5 and PM10 were exceptionally low across the board. PM2.5 averages hovered around 1.33 to 1.67 micrograms per cubic meters, well below the WHO limit of 5 micrograms per cubic meter. PM10 also followed the same highly satisfactory trend, with averages between 1 micrograms per cubic meter to 3 micrograms per cubic meter, which is well below WHO limit of 15 micrograms per cubic meter, ensuring a healthy breathing zone. Thermal comfort, humidity, and condensation. Relative humidity consistently averaged around 51% across the test point. This falls comfortably within the 50% to 70% benchmark, mandated by MS 1525 2014. Dew points also remain safely low, meaning there is zero threat of surface condensation or moisture damage. Based on MS 1525 2014, the recommended indoor temperature standards is between 23 to 26 degrees Celsius. Without air conditioning, the average temperature at point 1 to 5 were above the standard, ranging from 28 to 35 degrees Celsius, especially at point 3 due to solar heat gain. After the air conditioning was turned on, the average temperature reduced to around 22 to 26 degrees Celsius. Points 2, 3, and 4 met the standard, while some areas experienced slight overcooling or uneven cooling distribution. This thermal imbalance is directly tied to our air change analysis. When the mechanical air conditioning system was entirely switched off, reducing volumetric airflow rate and the air change per hour to 0, trapped heat had no escape. Without an active exchange to flush the space, indoor temperatures skyrocketed dramatically up to a maximum peak of 42.5 degrees Celsius.
performance, illuminance levels are measured at 4 different points under 3 lightning scenarios and compared against the MS1525 recommended standard of 300 to 500 lux for visual comfort. In scenario 1, the average illuminance was just 155.63 lux. At scenario 2, improved to average to 243.15 lux, but it still did not meet the minimum standard. Scenario 3 achieved an average of 182.85 lux, which also remained below the required level. As a result, the current lightning condition may contribute to extreme visual discomfort and reduce student concentration. 5.4 Acoustic environment. To ensure high accurate data collection, measurements are taken across 4 points under controlled conditions, focused on background noise level and reverberation times against the ANSI/ASA standard. First, for background noise, the standard sets a strict limit of 35 dBA. If the aircon turned off, the room have a range of 36.6 dBA. Since the aircon was switched on, mechanical noise pushing the average up to allow 45.4 dBA. So we found that average background noise level failed to meet the standard. Next, we've analyzed the reverberation time for our room value of approximately 821 cube meters. The recommended RT benchmark is 0.7 seconds. However, our recorded total average was an alerting 1.55 seconds. Undoubtedly, the combination of high mechanical background noise and prolonged reverberation significantly decreases concentration and communications.
6.0 Recommended solution. First, for thermal comfort, some area exceeded the recommended temperature range of 23 to 26 degrees Celsius, and the cooling distribution throughout the resource center was uneven. This caused discomfort, fatigue, and reduced concentration among occupants. To improve this condition, we recommend to improve airflow distribution. The air conditioning airflow supply should be rebalanced across all zones so that cooling can be distributed more evenly throughout the resource center. In addition, the diffuser direction and airflow rate should also be adjusted to ensure a more consistent indoor temperature. The second recommendation is to install solar shading devices such as blinds, curtains, or external shading system to reduce solar heat gains and help maintain a stable indoor temperature. Next, for relative humidity, the measured humidity level generally comply with the standard. However, regular inspection of the cooling system is still important to prevent moisture accumulation and microbial growth. In addition, better ventilation efficiency can help maintain healthy indoor moisture level. Moving on to lighting performance, the average luminance level under all lighting scenarios failed to meet the minimum requirement of 300 lux. This may cause eye strain, visual discomfort, fatigue, and reduced concentration among users. To solve this issue, we recommend increasing the number of LED lighting features in dim areas to improve the overall luminance distribution within the space. Besides that, the arrangement of lighting features should also be optimized and distributed more evenly to reduce unlit and overlit areas. Next is the acoustic environment. The background noise level exceeded the recommended standard of 35 dBA, while the reverberation time was also much higher than the recommended value due to harsh reflective surfaces and noise from the air conditioning system. As a result, occupants may experience reduced speech intelligibility, lower learning efficiency, and communication difficulties. To improve the acoustic condition, we suggest installing acoustic panel and acoustic ceiling material to increase sound absorption. Soft furnishings such as carpet and curtains can also help reduce sound reflection and reverberation within the space. Overall, the indoor environmental quality assessment at the FPE Resource Center showed that the indoor air quality was generally satisfactory. The CO2 concentration remained below 1000 ppm, while PM2.5 and PM10 concentration complied with the WHO guidance. Ventilation performance was also considered satisfactory. For thermal comfort, the air conditioning system successfully improved indoor temperature, but uneven cooling and overcooling was still observed at several areas. For lighting performance, the luminance level were generally below the required 300 lux standard. Uneven lighting distribution affected visual comfort. Meanwhile, for the acoustic environment, the background noise level exceeded the recommended standard, and the reverberation time was excessively high due to reflective surfaces. In conclusion, although the resource center achieved acceptable indoor air quality, improvements are still necessary in terms of thermal comfort, lighting, and acoustic to provide a healthier, more comfortable, and productive learning environment for users.
Through proper use the measurement apparatus to evaluate indoor environment quality, I also gained a better understanding of the field standard and learned several improvement methods to achieve lighting and acoustic performance in the learning environment. Through this project, I learned how.
In reflection, this report highlights that while our air quality is excellent, true indoor environmental comfort requires a critical balance. Moving forward, designing for passive thermal resilience is essential to reduce our absolute reliance on mechanical systems.
From this assignment, I learned how different IEQ elements such as thermal comfort, lighting, acoustic, and indoor air quality are connected to each other. This project gave me better exposure to real site analysis.
From this project, I learned how building science theory are applied in real-world assessment and how important technical accuracy is for a quantity surveyor.
Overall, the IEQ assessment helped identify the strengths and weakness of the indoor environment. and providing useful recommendations for future improvements.